And hello, welcome back to this video on turbulent heat transfer. So thanks for tuning in. So last time we talked about this assumption we made for the turbulent boundary layer, where we say that this quantity here is on the order of magnitude of 1. Of course, when let's say you have momentum diffusing way faster, the momentum turbulent transport is much more than the temperature turbulent transport. I need to say that, okay, maybe the viscosity is much more than the thermal conductivity, which means that high Prandtl number. Then you'll find that this quantity may indeed be more than 1. Okay, pardon me, sorry. If you're okay, I'll rather think of it this way. Normally we assume Prandtl numbers on the order of magnitude of 1, so that this assumption holds. But of course you want to think, if your Prandtl number is ultra high or ultra low, what happened to this quantity here? Okay, so one way of thinking of it is that if your Prandtl number is high, okay, this is one way of thinking of it, it's not a official way, so to speak. Okay, what happens if Prandtl number changes? What is its effect on the turbulent Prandtl number? PRT. So, okay, if your Prandtl number changes, if Prandtl number PR is low, means heat flows through the fluid very easily compared to momentum, i.e. liquid metals. Okay, so this is an ultra low Prandtl number fluid like liquid sodium, liquid lead, etc. etc. What will happen to the temperature fluctuations? T prime. What will happen to the temperature fluctuations? If the fluid medium is so conductive, then you would say that the temperature differences tend to be small. T tends to be small in high conductivity or high thermal conductivity environments, right? T tends to be small in high thermal conductivity environments, or the temperature fluctuations tend to be small because before there are temperature fluctuations, the temperature differences, they'll drive a lot of heat transfer, and then you'll minimize these temperature differences anyhow, right? So high thermal conductivity environments do not sustain very high temperature gradients by and large, especially, let's say, I'll just illustrate it here. Let's say you have this random temperature fluctuation here, and this is the bulk temperature. In the high conductivity fluid, this heat will actually flow out, and then you'll make the temperature fluctuation on average smaller. If you have a very insulating fluid or high Prandtl number, is a low Prandtl number, the high Prandtl number fluid, what happens if you have a temperature fluctuation? I mean, you will still conduct heat away, but very slow. So this is maybe what your curve would look like, rather than you have a small flat shape on average. Okay, on average this is flatter. Okay, on average sharper. Alright, so T prime tends to be bigger in low Prandtl number fluids, or smaller in low Prandtl number fluids. So you can think of it like this. So if you have a sudden fluctuation in temperature in this fluid, you have a sudden fluctuation in temperature in the fluid, which one is more likely to sustain that temperature difference on average? So a high Prandtl number fluid with more insulating capability, more thermally insulating, will tend to sustain those temperature differences higher on average. So higher temperature fluctuations on average will result in this term being high. So it's more likely that this, okay, if Prandtl number is high, then this term at the bottom tends to be bigger. All right, for a constant whatever term this is here, the Reynolds stresses. For constant Reynolds stresses, this term will be higher. Okay. If the Prandtl number is low, then for constant Reynolds stress, this temperature fluctuating term is lower. Alright, so otherwise, if they are more or less equal, you can just assume it's 1. But in reality, this would be some function of a Prandtl number. Alright, in reality. Okay, so just want you to take note of that as we go. So high Prandtl number means this is low. It's like inversely proportional to the Prandtl number. Hope you understand why. I mean, how I'm considering it. I'm considering, let's say, for constant Reynolds stresses. If you have a high Prandtl number fluid as compared to a low Prandtl number fluid, how will this quantity change? So this, I'm using the argument that high Prandtl number can sustain temperature fluctuations more on average as compared to the low Prandtl number, because thermal conductivity, it kind of plays a role. If everything else is constant, the thermal conductivity kind of plays a role in how quickly this temperature difference is being temperature fluctuations are being dissipated. So I would say that this quantity is actually inversely proportional to Prandtl number. Okay, but for now we just assume that it is 1. If Prandtl number is close to 1, so we can just live with that. So how then do we find the Prandtl number or turbulent Prandtl number in this simplified version? Okay, in simplified form. Okay, how do we find this turbulent Prandtl number? Okay, so we go back to our relation here, and then we find, oh, okay, this dt dy and du dy, we can find it near the wall. All right, we can find these near the wall. We can find the resolved temperature gradients near the wall. Okay, so experimental data actually provides a law of the wall. As you recall, the log law region has this kind of correlation. For temperature, we have something similar we can derive. Okay, so temperature also has a log law. Okay, and of course these are in non-dimensional coordinates, so we kind of have to change things up a little bit. Okay, we have to change things up a little bit. So we have to change this thing to be in terms of wall coordinates as well. Now this is okay, this is one of the correlations, and it's actually valid from the Prandtl number equals to 0.7 to 100. Okay, then this correlation actually holds. All right. Okay, so this is a small range of Prandtl numbers, like from order of magnitude 1 to order of magnitude of 100. If this doesn't change, then sure, So how it must be, I guess, 1,000 times or more difference for this effect to start kicking in. But it looks like from experimental data for this range, you can use this correlation here, no problem. Okay, so now we want to non-dimensionalize our Prandtl number equation. So how so? So one thing we note is that we can start using this T plus. T plus is actually T minus T naught. So T naught is some reference temperature, for example, your wall. T is the local temperature of wherever you are considering at some point in Y or whatever. Yeah, T star is actually what they call like the in some sense the friction temperature. What is the friction temperature here? Okay, friction temperature is the heat flux, which is over here. Heat flux over rho Cp times the friction velocity. So this is how we sort of measure this friction temperature. Why is this important? Remember V star, okay, the friction velocity, so tau, and this is actually tau wall over the density, right? This is tau wall over density, just to remind you. Okay, yeah. And of course, the way we non-dimensionalize y will be as the following: y plus equals to y u star or y v star. However, you just know that it's the friction velocity. Okay, or y u star. Sorry. Yeah, u or v. Maybe I'll just change it to u. I'm way more used to u anyway. So anyway, y u star over nu. Okay, so this is how we do it. So notice that we use this wall shear stress as some reference quantity for the velocity. Likewise, for temperature, we use the wall heat flux. Okay, Q wall. The wall heat flux as some reference quantity for this thing. Okay, so Q wall over rho Cp, that will actually give you that so-called reference. Okay, because you see here, tau wall is divided by rho. Equivalent for heat flow is Q wall over rho Cp, some sort of that. Because you have this thrown in as well, so this will help you to non-dimensionalize your equation. So we apply these relations in. Of course, we can say dy and dy is basically dy plus over dy plus because it's just a constant. No problem. Okay, this is just a constant, so no problem. We'll just leave it as that. The interesting thing is, of course, this u and this t. All right, this u and this t. So we can sort of. So anyway, let's see how this actually plays out. Okay, so we have a t over t star, or we say that we can change this into some sort of we can change dt. Okay, let's start with temperature. dt dt or dt bar is actually equals to just the t bar minus t reference t naught. So in this case, t naught we like to say is a wall temperature. It can be a wall temperature or it can be some infinite temperature here, T infinity. Well, I mean, whatever floats your boat. Importance is of course this temperature gradient, but okay, it can be written as such just based on differentiation, but I would prefer to use wall temperature because all of this is actually, you want to kind of keep it with reference to the wall. And what else then can we do? We need to non-dimensionalize. Okay, so t minus t naught equals to t plus and t star. All right, let's do that. Okay, we apply this equation in here. Okay, so what I'll do is just get this over to the other side here and over here. So let me copy and paste this down, and what we get is t plus t star. T plus t star. T star is for us is a constant, so t star just comes out. T star comes out. dt plus. Alright. Likewise, du can be regarded the same way. Du actually is regarded the same way. And actually again, the importance is the not the temperature, the velocity difference, right? Okay. If you have, of course, if you have a wall that's moving at 500 meters per second here, and then the fluid is also moving at 500 meters per second. Okay, both of them are moving at 500 meters a second. It is actually the same as a wall at 0 meters per second, and the fluid also moving at 0 meters per second. So what is actually important is the relative velocity. Similar to how for temperature, the importance is the relative temperature between the wall and the fluid. This is actually the relative velocity between the wall and the fluid. Except, of course, in most of our cases, in our fluid cases, it's easy to set our wall temperature, wall velocity to 0. Well, that's a natural reference, reference velocity anyhow. So it kind of skips a bit of the steps. But I'm just trying to say, putting a T naught or T wall over here is actually yeah, it makes sense. There's a relative change in temperature, which is driving some heat flow, and likewise there is a relative change in velocity, which is causing some diffusion in momentum. Okay, same way. So du, again, we'll do the same thing over here. It is I'll use u star here for friction velocity. U star, the u star, and u plus. Okay, so when I get this u star out, and u plus, and get this u plus out. All right, what do we get? Okay, so let's put this into here. So let's put this here. Okay, I will just equate it as such. dt minus t wall, so we'll have a dt plus here. dt plus, and then we will have a t star on the outside. And then we'll have u star at the bottom. Okay, so yeah, let's try substituting some values in. Alright, t star over u star, that seems to be an important quantity. T star divided by u star, what is that equal to? Okay, it's a q wall over blah blah blah, and then you kind of divide it by 1 over u star. Okay, u star. And then what you get at the end of the day is just this quantity here. Alright. Now, of course, the first thing, yeah, you'll get this kind of expression, and now the first thing you say is, hey, these things are not exactly the same. The units are not consistent, right? The units are not consistent, and you'll be right on that. So to really kind of make the units consistent, we need to consider the more original equation of this Prandtl number thing, right? So we'll have this over here, and what we say is, okay, this thing on top, I can replace it by these two. Okay, replace it by this on top and this on the bottom, and this t star over u star, we can also say it's equals to this quantity over here. Alright, and then you put those dimensionless temperature gradients down. right? Yes. So once we do that, we see that, okay, we look at something very familiar. Q wall over rho CP, and you can compare to this new V prime T prime, and you see that this unit actually cancels out with this. This U star will cancel out with this fluctuating part. Okay, so this is how the non-dimensionalization works. So let me put this down here and put this down here. Okay, there should be a U star here, U plus. Okay, there we go. There we go. All right, so how does the non-dimensionalization work? It works like so. All right, we have this U prime V prime. Okay, we have this U prime V prime over this U star squared, and then we'll have this V prime T prime divided by Q wall over rho CP. CP, and there we go. Yeah, looks pretty convoluted with so many fractions, but let's put some nice brackets to try and make it a little more orderly. So this is actually the result of our non-dimensionalization. Okay, so yeah, again we will have this thing over here compared to this thing over here. This fluctuations in the momentum as compared to the friction velocity, fluctuation in the temperature as compared to some thermal diffusivity kind of quantity. I mean the heat of the wall divided by rho and Cp, which is, I think, yeah, it's pretty much in the same units as, you see this thing, and then yeah, this quantity kind of pops up again, and then at least the same units, these units and these units are consistent, and pretty much it's consistent with yeah, it's consistent with these units, so it should give you the right units. Okay, so nonetheless, yeah, we still you know, kind of have to measure. I mean, there's a reference friction velocity and some heat flux, which you can kind of vary very arbitrarily. Okay, because of course if you have a higher heat flux, you might have more temperature difference to play around with, and that may lead to more temperature fluctuations in general, and steeper temperature gradients overall. But yeah, I mean, the explanation on, I mean, the way we can think about this relationship between this quantity and this quantity still remains, even though they are non-dimensionalized to an extent, because again, if your Prandtl number is very low, your heat fluctuations will still not, I mean, this quantity will still be smaller as compared to this. So and Prandtl number doesn't affect this wall friction as much compared to this wall heat flux. Okay, because the wall heat flux, you can kind of prescribe it almost arbitrarily, and wall friction is more a function of the Reynolds number. So these two can be varied independently of each other, but the ratio between this and this is still kind of somewhat dependent on the Prandtl number. But you find the dependence is actually pretty weak. Okay, but it's important when the Prandtl number changes by huge orders of magnitude. Okay, so once you have this, we can start plugging in this dd plus dy plus du plus dy plus in the form of these wall functions. All right. So if you take a look, the t plus dy plus, it will be this. I mean, you can do a differentiation over there, but okay, I will stop now and I can continue in the next video. Thanks for watching.